In our previous video, we learned how to solve linear equations, starting with two-variable equations, like figuring out the cost of apples and parking fees using simple lines on a graph. Then we tackled three-variable equations by adding another dimension, apples, mangoes, and parking, transforming our graph into a 3D space. But manual solving takes time, so we automated it with Python. First, we broke down the process into two main steps. The eliminate function eliminates variables from top to bottom, simplifying the equations one by one. Then, the solve elimination function works from the bottom up, calculating each variable's value using back substitution. Finally, the solve function ties it all together, eliminating, substituting, and giving us the solutions. Linear equations produce straight lines, but what if the relationship between variables forms a curve? That's where quadratic interpolation comes in. It enables us to fit a smooth curve through a set of points. The general equation for this is y equals ax squared plus bxc. Let's use an analogy to better understand this concept. Imagine you have a website, and there are limited servers to control the traffic on it. Increase in traffic causes server overload, which shows the need for efficient traffic prediction. Let's analyze a dataset to explore it. Here's a table showing a dataset. The input is the time, and the output is the traffic. The time tells us when people are visiting the website, and the traffic tells us how many users are on it at that time. Notice how the traffic increases as time goes on. The relationship between time and traffic follows a specific pattern that can be described using a second-degree polynomial. We'll use this pattern to predict the traffic when time equals 4. Now, can you figure out the value of traffic at time equals 4? Take a moment and think about it. Not sure where to start? Here's a hint to help you out. Think of traffic as being described by the equation a times time squared plus b times time plus c. Your task is to determine the values of a, b, and c using the data from the table. All right, ready to check your solution? Let's walk through it together. Now that we have the general equation, we'll use the data from our table to create specific equations. By substituting the values for time and traffic, we can form three equations. For the first row, where time equals 1 and traffic equals 6, we substitute these values into the equation, giving us a times 1 squared plus b times 1 plus c equals 6. We repeat this process for the other rows, for time equals 2 and traffic equals 12, and time equals 3 and traffic equals 20, giving us two more equations. Now that we have the three equations, let's move forward and try to frame the fourth one. We already know the pattern these equations follow, so we can use the same approach with time equals 4 to create another equation. Do these equations remind you of the ones we solved with the elimination method? Take a moment to notice the pattern. These equations are just like the ones we solved before with the elimination function, so we can simply recall the function to get the solution. Here's the output, showing the coefficients a, b, and c. Using these values, we can now calculate the traffic at time equals 4, which gives us the value, traffic equals 30. Let's make this process a bit more automatic. We can express the traffic equation as a matrix multiplication of two things, a row vector and a column vector. But wait, before we move on, let's take a moment to familiarize ourselves with matrix, vector, and matrix multiplication. Matrix is a singular term, while matrices is plural. A matrix is a rectangular arrangement of numbers, symbols, or expressions, organized in rows and columns. It is like a table where each entry or element sits in a specific spot based on its row and column. For example, a 2x3 matrix, where 2 indicates the number of rows, 3 indicates the number of columns, and 2x3 represents the order of the matrix. Matrices are used in mathematics to represent data, solve systems of equations, and to perform transformations in areas like physics, computer graphics, and more. A vector is a one-dimensional list of numbers. It can either be a row vector or a column vector. Row vectors have an order of 1 by n, while column vectors are n by 1. For example, here's a row vector and a column vector. You might wonder, what's the difference between a matrix and a vector? Matrix is a 2D grid of numbers, while vector is a 1D list of numbers. Matrices have multiple rows and columns, while vectors have only one row or column. Finally, a matrix is described by its order, like 2 by 3, while a vector is called either a 1 by n row vector or n by 1 column vector. From this, we see that vectors can often be thought of as a special case of matrices. Matrix multiplication is a method of combining two matrices to produce a new matrix. It involves multiplying the rows of the first matrix by the columns of the second matrix. For example, in this case, the row matrix has order of 1 by 3 and column matrix has order 3 by 1. Hence, we obtain a scalar, a single number. The general formula for matrix multiplication is expanding the terms gives us the sum of each element's product. Let's pick up where we left off. Our goal is to automate traffic calculation for the desired time. So let's start by breaking down the matrix multiplication of the traffic equation, step by step. First, we start by multiplying the constant a by time squared. Next, we multiply the constant b by time. Lastly, we add the constant c to complete our equation. Now that we understand matrix multiplication, let's move on to coding it with our multiply vectors function that accepts two inputs, vectors a and b. Vector a contains the values of a, b, and c from our traffic equation, which we calculated using the elimination method. And vector b is made up of numbers we get from time equals 4. First the square of 4, then 4 itself, and finally the number 1. These values are given as input when we call multiply vectors function. We then initialize an empty list out for our products. We'll iterate through vector A, multiply corresponding elements from A and B, and store the results in the output list. We start with A0 and B0, multiplying 1 and 16. The product 16 is added to the outlist. Now we move to the next pair, A1 and B1. Multiplying 3 by 4 gives us 12. We add this 12 to the outlist. Finally, we take the last pair, A2 and B2. Multiplying 2 by 1 gives us 2. We add this 2 to the outlist. Once we finish iterating through both vectors, the outlist contains all the products, 16, 12, and 2. Finally, we sum these values, 16 plus 12 plus 2, giving us a total of 30. That's how we multiply vectors in Python. As we explore polynomial fitting, a key question emerges. How many distinct data points are needed to fit a polynomial of degree n? Reflect on the options displayed. The correct answer is n plus 1. Wondering why it's n plus 1? Let's explore with some examples. Consider a 1-degree polynomial, y equals ax plus b. To find both a and b, we need 2 points, each providing an equation for the two unknowns. So for a degree 1 polynomial, we need 2 points. Now let's look at a polynomial of degree 2, represented by y equals ax squared plus bx plus c. For this equation, we have 3 unknowns, a, b, and c, so we need 3 distinct points to generate 3 equations and solve for each unknown. Therefore, 3 points are needed for a degree 2 polynomial. In general, for a polynomial of degree n, we write it as y equals an times x to the power n plus an minus 1 times x to the power n minus 1 plus an minus 2 times x to the power n minus 2 and so on, down to a1 times x plus a0. We have n plus 1 unknowns, so we need n plus 1 points to uniquely determine the polynomial. Note that the coefficients an minus 1, an minus 2, and so on function similarly to a, b, and c. Let's take it a step further. Solving these equations manually becomes harder with higher polynomial degrees or more data points. It requires significant effort. Even small errors can lead to entirely incorrect results and would be very time-consuming. Therefore, instead of solving manually, we'll automate the process using Python, ensuring faster and more accurate computations. In the previous video, we manually created the matrix of equations, and provided it as input to extract coefficients and calculate the result. Today's code makes this process much simpler. Instead of manually constructing the matrix, we'll only need to input the data and the prediction point. The code will handle the rest. We have time values and corresponding traffic values, and we know that they relate through these equations. But how do we solve these equations effectively? Computers can't solve equations directly in this format because they involve variables, which are symbolic and abstract. Matrices, on the other hand, represent equations numerically, eliminating variables and enabling efficient computations through matrix operations. To do this, first we create each equation in matrix format. This occurs sequentially. Traffic values are added, followed by time powers. So our first objective is to transform these equations into matrix form. We'll use two loops, one to add traffic values and another to calculate time powers, storing everything in a matrix. Now that we have the equations in matrix form, we can find the coefficients a, b, and c, that is the column vector in the traffic equation. So the second goal is to extract the coefficients from the solved matrix. Now, let's prepare the time vector to predict traffic at time 4. It starts with an initial value of 1, followed by 4, and then 16. These correspond to 4 raised to the powers of 0, 1, and 2, forming the vector with values 1, 4, and 16. So our third goal is to prepare the vector containing time and time-squared values. Finally, we calculate the traffic value at time equals 4. To do this, we multiply the coefficients column vector with the time and time-square row vector. So, our fourth and final objective is to perform matrix multiplication on the two vectors. This gives us the traffic value we need. Now that we've understood the logic, let's keep this note handy when we dive into the actual code. In our last video, we explored how the eliminate and solve elimination functions work. Here's a recap on how the solve function operates. It first calls the eliminate function, which performs elimination to transform our system of equations into an upper triangular matrix. The solve elimination function takes over next. It back substitutes the values from the triangular matrix to find the solutions for each variable. Together, these two steps solve the system of equations and return the coefficients of the polynomial. Now let's move to the solve polynomial function. We start by defining an empty list equations to store our equations. This is where we'll create our equations in the matrix format based on the input, x and y, which represent time and traffic, respectively. Let's start with our first goal. We will loop through each value in x and y to generate equations in matrix form. As we generate this matrix, the original equation will be shown simultaneously above the equation's variable for your reference. For the first iteration, when x0 equals 1 and y0 equals 6, we start by creating an equation list, beginning with the initial value at y0, which is the traffic value from the first equation. Next, we introduce a variable x_f, which will store the powers of x representing time and time-squared values, with the initial value as 1. In the first iteration of the J-loop, x_f starts at 1. The first power of the time value, which is 1 to the power 0, is added to the equation. Then x_f is updated by multiplying it with 1, which is 1, making x_f equal to 1. In the second iteration, the next power of the time value, 1 to the power 1, is appended to the equation. x_f is multiplied again by 1, resulting in 1 square. In the third and final iteration, the highest power of the time value, 1 square, is added to the equation, and x_f is updated again. Next, we reverse the equation to align the powers of x properly, such that the highest power comes first, and then add it to the equations. In the second iteration, with x1 equal to 2 and y1 equal to 12, we begin by updating the equation list with the value at y1, representing the traffic value from the second equation. We then update x_f to store the powers of x for this iteration, starting with the initial value as 1. In the first iteration of the J-loop, x_f starts at 1. The first power of the time value, which is 2 to the power 0, is added to the equation. Then x_f is updated by multiplying it with 2, which is 2, making x_f equal to 2. In the second iteration, the next power of the time value, 2 to the power 1, is appended to the equation. x cof is multiplied again by 2, resulting in 2 square. In the third and final iteration, the highest power of the time value, 2 square, is added to the equation and x cof is updated again. We then reverse the equation and add it to the equations. In the third iteration, with x2 equal to 3 and y2 equal to 20, we continue by adding the value at y2, representing the traffic value from the third equation, to the equation list. We then carry forward the x cof variable to store the powers of x for this iteration, starting again with the initial value as 1. In the first iteration of the J loop, x cof starts at 1. The first power of the time value, which is 3 to the power 0, is added to the equation. Then, x cof is updated by multiplying it with 3, which is 3, making x cof equal to 3. In the second iteration, the next power of the time value 3 to the power 1 is appended to the equation. X cof is multiplied again by 3, resulting in 3 square. In the third and final iteration, the highest power of the time value 3 square is added to the equation and x cof is updated again. We then reverse the equation and add it to the equations. We have achieved our first goal and successfully created the equations in matrix form. Let's proceed towards the next goal. We'll pass the system of equations to the solve function, which would calculate the coefficients a, b, and c. In our example, we get the values a equals 1, b equals 3, and c equals 2. We have achieved our second goal and obtained the coefficients a, b, and c. Let's proceed towards the next goal. We start by defining two variables, xpows and xpow. The xpows matrix will store the powers of xp, which is the time value where we want to calculate y, here given as 4. The xpow variable will hold each power of xp starting from 1. We begin the first step with k equal to 0. We add the current value of xpow, which is 1, to the xpows matrix. Next, we update xpow by multiplying it with xp, which is 4. The new value of xpow is 4. In the next step, with k equal to 1, we add the updated xpow value to the xpows matrix. We then multiply xpow by xp again, updating its value to 16. Finally, for k equal to 2, we repeat the same process, adding the current xpow value to xpows and updating xpow. Multiplying xpow by xp once more, the final value becomes 64. This is calculated automatically by the code, so we won't be using 64 in any calculations. After the loop completes, we reverse xpows to get the correct sequence of powers. We have obtained the time and time squared values for time equals 4, accomplishing our third goal. Let's proceed towards the last goal. Now that we have both vectors, xpows and coef, we can use them to calculate the final result. Starting with the first coefficient, 1 multiplied by 16, the first power in xpows. Next, we add 3 times 4, the second power in xpows. Finally, adding 2 times 1, the last power in xpows, to complete the calculation. The polynomial's value at x equal to 4 comes out to be 30. By multiplying the two vectors, we were able to calculate the traffic value at time equals 4, reaching our final goal. Before we wrap up, here are a few questions for you to try on your own. In this video, we took a deep dive into quadratic interpolation, a method used to fit a curve through data points using the equation y equals ax squared plus bx plus c, where a, b, and c are constants. We started by understanding the quadratic equation and how it differs from linear equations, producing curves instead of straight lines. To bring this concept to life, we explored a real-world example of website traffic prediction, modeling the relationship between time and traffic using a quadratic equation. We defined the equation as traffic equals a time squared plus b time plus c, and derived a system of 3 equations by substituting data points. This allowed us to solve for the coefficients a, b, and c, crucial for predicting future traffic. We then introduced matrix and vector operations, showing how quadratic equations can be represented through matrix multiplication. To strengthen this understanding, we explained the difference between matrices and vectors. We walked through examples of degree 1 and degree 2 polynomials, highlighting the key principle that a polynomial of degree n requires n plus 1 points to determine its coefficients. Finally, we automated the entire process using Python. We defined vectors for time and traffic, let the code handle matrix multiplication, and efficiently calculated the traffic prediction for time equals 4, arriving at the result of 30 users. In the upcoming video, we will explore how to handle situations where the curve doesn't fit the data perfectly.